Welcome to another video about smart technology. The goal of this video is to talk about the HSE network, high-speed Ethernet, which is a network that provides the interconnection of industrial automation equipment over an Ethernet network. The HSE Ethernet network, that is the high-speed Ethernet network. High-speed network for controlling processes, ensuring fast process control. No megabits. Has as its main objective connect controllers and computers and equipment in general in digital network applications for industrial automation. Now we will talk about its components. The computer, which is the host device, is your component for configuration and maintenance. So, it's one element, main ones of the HSE network. Detailing a little more, so we have the host device there. That equipment acts as a configuration station, like a platform for setup, a supervision station, a maintenance hub. Basically, that's the computer we use. The link device is the equipment that will create the bridge. It will make the connection, hosts Ethernet network, and connect the channels of the field equipment. As examples of connection devices, we possess the ADF-ME-A2 with an Ethernet channel, safety, and 4 HI channels for the Foundation Fieldbus network. Another example is the ADF-ME-A3 equipped with 2 HSE Ethernet channels. By having redundancy, the system provides 4 HI field channels specifically for Foundation Fieldbus, totaling 94 characters. Another part of the HSE network is I/O gathering. It can be a device for data acquisition and conventional digital or analog inputs and outputs. As an example of I/O gathering, the DF73 stands as an illustration among others, the DF95 as well, that are controllers like Profibus or controllers. For example, the LC800 and DF75 models are included. The programmable controllers, DF89 for programmable controllers, DF designed with ladder or block diagrams for programming. They are standard equipment or network capable equipment, but they do not belong to Foundation Fieldbus. Another component of the HSE network is the FD, which may include field devices such as transmitters and also positioners. For example, FD includes field devices such as transmitters. Foundation Fieldbus, interconnected directly to the Ethernet network, such as the LD302, the TT302 from the Foundation Fieldbus family. They are generally devices that include functional blocks that can be modified to accommodate different control tactics. After discussing all the components of an HSE network, we will discuss the architecture briefly. We can have vertical communication among all the components of the HSE network with the computer, and also horizontal communication between HSE network devices. Hence, the HSE system allows for data communication horizontally or vertically, getting data from the field and bringing it to the management area, to the service area, to the maintenance area. Due to bidirectional data communication, we have extensive exchanges of information. We now show this communication in all directions. A data transfer, exchanging information between computers, controllers, and field devices. We present the HSE architecture here, using System 302, thus having 16 characters, where we find the Syscom configurator that will establish the networking and management strategy for our system, where communication is established with the HSE OLED server of the Ethernet TCP and IP network, communicating there also with the TCP and IP link devices, the HSE stack, and specifically with the HUM, communicating the 4 HUM channels, Foundation, Fieldbus, and their data interconnection. Now we will cover some application scenarios. One situation involves devices communicating on the same channel, sharing information with each other. Devices are able to communicate with each other while connected to the same channel, exchanging data and information. Another notable application scenario is data swapping between channels. We can have 4 channels in a DF-MIA3 bridge, and we can swap this data information between channels. Another notable scenario is data exchange between CPUs or between equipment that are connected to different bridge channels. So this data exchange scenario is quite interesting as well. The data connection between internal and external links of the HSE architecture. Thus, we can exchange data from a link device or a bridge between I/O gateways and link devices and make this data exchange. Another case is the external link between devices in the HSE network and HUM field instruments. Hence, we can make the exchange between equipment data and also particularly exchanging links externally or internally, as we discussed earlier. Another notable scenario is the data connection with the Internet, employing another pillar of the Internet industry, switching to IoT communication through the Internet and allowing communication between equipment wirelessly through Internet usage. So, this is a scenario that makes use of this significant pillar of the Internet domain. In the HSE network, it's possible to implement redundancy to ensure fault tolerance. Hence, from the host's point of view, the network and equipment are shared. Redundancy is employed to ensure high availability of the plant, any card, interface, or the Internet can have media redundancy. So, the HSE supports network redundancy as well as equipment redundancy. Here we show a configuration with 2 stations. We illustrate a scenario with 2 switches and a setup with equipment, controllers, and the field setup. We could have in one of the networks in red an HSE Ethernet system connected to a primary switch and a secondary switch. In blue, we could have another HSE connection. The CPU of SMARA from the F series comes with 2 HSE inputs, thus allowing to achieve the Ethernet redundancy. In the event of a failure in a red system, we could have the redundancy in blue in a second Ethernet network option. In a network using HSE with redundancy, we are able to publish messages for diagnostics, exchanging info not only on data, but also diagnostic data in a redundant network. Therefore, the diagnostic messages share the view that a device perceives of all other devices that are part of the redundancy strategy. All will gain a view of the redundancy and the system. Here is the individual view of the network, where devices are exchanging data among themselves, sending and collecting over Ethernet channels. In the case of a channel failure, we maintain communication via another channel, Ethernet, without losing data. Hence, every device that receives a diagnostic message refreshes its HSE routing configuration and applies this information to verify the network route taken by the device that transmitted the diagnostic message and determine its path correctly, with this making the redundancy of the system. In another case of redundancy, we can achieve redundancy for the equipment, controller, and link device. We possess our primary device along with a secondary device in case of backup, and we can configure the secondary device in case of primary device failure. Takes on a few link device network duties. Then automatically something can change from one device to another device.